Well, I'm very happy to be here and glad to get the opportunity to be part two of last night's talk, which you don't usually get that opportunity when you don't have the time at the end of the talk. And it's not really part two, but it does extend some of the things I began to mention in my talk last night. I know at least one person here was there. So, what I'm going to talk about is a very tricky subject because, on the one hand, the mathematics of probability is an extremely important thing. My talk last night was how it's so widely relevant to so many aspects of the natural and biological worlds that it's an indispensable way for understanding things. On the other hand, when it's put to use in science as a way of making judgments on whether a particular experiment or study has discovered anything reliable or not, it is just really very widely misunderstood and misused. And so I guess I should start out by saying that I don't mean to offend the mathematics itself, only the people who misuse it. So anyway, to start out, here's a typical sentence that you might read in a newspaper. This was out of a story in a newspaper. The results found that amandia raised the risk of heart failure, but not to a level of statistical significance. You know, I don't mean to cast aspersions on all journalists, of course, because some know better, but this is way too common. I mean, it's just self-transparently dumb, and it's even, hard to explain it sometimes to the writers who do this. It's really incredible. But it's not statistically significant. You don't know that it was Amandia that did the raising. You can phrase it in the group with Amandia, there were more heart attacks, but not that. If it's not at a level of statistical significance, obviously, you don't know why it was higher in that group. You haven't produced the evidence to make any conclusions. So this is like what I call the elementary first level problem. Is a total lack of understanding of anything. But the real serious problems, it gets trickier than when you point this out to a writer, and the writer then wants to know what does statistical significance mean, and then it gets really tricky. So I mentioned this paper last night as an example of some of the problems in science and misuse of statistics. This is a paper that was published about 3 or 4 or 5 years ago now, I think, in PLOS Medicine. And as I indicated last night in my talk, it's not itself immune to its own charge against other papers. It's not unflawed in its analysis. And nevertheless, the point that's being made, whether the claim here is that he has been able to demonstrate by going through a series of possible reasons why studies are wrong, that the majority of studies are wrong. And there are several points in his line of reasoning that are questionable. But nevertheless, if you talk to people and look at this sort of thing and look into it, while they may disagree with the way he went about demonstrating what he said, they do agree with the basic point, which is a large proportion, if not a majority, of scientific studies, individual studies reporting claimed conclusion results, are not in fact correct. Science, and this is a point I'll be getting to that afflicts science journalists in a very serious way, because science itself maybe can survive this kind of thing, because scientists all know you have to reproduce your results, and it's only over results being reproduced over time that they become well accepted. Journalists take the first thing that comes along and write a story about it, and here's something scientists discovered. So that creates an automatic problem right from the beginning. So anyway, that paper, it's really one of the papers that got me thinking about these issues more deeply and really looking into it and trying to figure out how to deal with the issue of statistical significance when you're writing about science results in the media. Most of you probably are all familiar where the system of doing studies and null hypothesis testing and calculating to see the statistical significance originated with people like Fisher, who back in the 1920s really started emphasizing these methods, and then Naiman and Pearson, who kind of reinterpreted how you should interpret what was going on with statistical tests. And see, this is not, we're cutting off the top of the thing. Let's see their names.
Yeah.
There might be at some point in the talk something important along the top.
You never know.
You keep going. Anyway,
I don't know if we can do that.
the point is that the origins of the methods that are now used came out of people who had competing points of view about how things should be done. And as near as I can tell, and based on what other much more knowledgeable people than me have written and said, what emerged was kind of a hybridization of these approaches that ultimately it makes it very difficult to trace it down to any rock-solid foundation. And that is one of the things that makes it difficult to explain to people what's going on, because if you really start analyzing what's going on with this, you ultimately get to the point where you don't have any legs to stand on. I mean, it's just not a system that is built up on a solid foundation. Over the years, a number of people have commented on this system, on the problems with this system. A number of statisticians and scientists and other observers who have looked at what goes on with the whole business of null hypothesis significance testing have commented in similar, goes back to 1960, which is one of the early comments to this effect. This method, the significance testing is based upon a fundamental misunderstanding of the nature of rational inference. And that's a problem if you keep using it for rational inference. Steve Goodman at Johns Hopkins over the years has written a series of papers that have tried to call attention to the issues and problems of using p-value significance testing and that sort of thing. I just have to do this to establish the fact that I'm not the only person who I didn't discover this problem all by myself. I went for decades wondering why I couldn't understand statistics, and then I figured out it's because they don't make sense. And of course, the problem is not, with statisticians. Most statisticians are aware of these issues. It's the scientists who take their data and put them into a software package and get a number that can spit out p equal 0.05 or whatever and say, oh boy, I can publish and I can continue, but they do not understand what it is that those numbers actually mean. Even they've either not really had that kind of training, or they've had a course where it was just the mechanics were taught, but not the underlying rationale and all that stuff. Anyway, so you get this, and this is, I think, time and time again, I have found this to be the case with people I've talked to and scientists and all over the place, that these guys say many investigators, I've had many other people tell me most investigators do not really understand what statistical significance really means. So, when I talk to, the first thing I tell other journalists and my writers who write for me and everything is that you, first of all, got to clear up this use of the word significance. It doesn't mean significant in the way that English language usually uses the word significant. This is a critical point to understanding what's going on here. And you see phrases like this in newspaper articles. Those who took the drug did not have a significantly higher rate of bowel problems than those who don't. That is not correctly phrased. They did not mean that it was a significantly higher rate in the sense of the ordinary use of the word significant. They meant there was a statistically significant difference in the rate. It's just not the same thing. The statistical significance, and for explaining this to reporters and getting them to be clear on this is really a problem, because I think, well, but if it's a bigger effect, it would be more statistically significant. That's not the issue here. Is not about magnitude. Is it statistically significant or not? And is it statistically significant or not is not a question of the magnitude of the effect. Level of statistical significance is not the same as magnitude of the effect. And of course, the reason that, if you start getting into it and you explain to people, I mean, the sample size is a powerful determinant of this level of statistical significance, regardless of the size of the effect. You can have a very, very, very trivial effect in terms of a real but small effect. If you have sample sizes of 100,000, that will come out to be statistically significant, even though in terms of actual practice or clinical practice or wise medical choices, it would not be something that would cause anything that would be worth making a change in policy over. So these are issues that are, again, these base level issues in getting the media to understand what they're doing. But I said that. All right, so then this is a little segment from a talk I gave on a panel at a statistics meeting about statistics in the media, and I was trying to show statisticians how hard it is for journalists to understand what statistical significance means by saying that if they ask a statistician, or somebody will say that's what it means, and then the journalist will not have a clue what you're trying to say. So people then will start trying to explain to you what it means. And they'll say, well, it means something like this. And then, of course, the statistician will say, that's wrong. And then they'll say, oh, then that must mean that. And they'll say, no, that's wrong. And then, or maybe they'll translate it that way. And, of course, that's also wrong. So, but these are statements you hear all the time from people trying to explain to people what statistical significance means. These are not correct statements, but they are the way it gets translated, and most journalists, I would say, would not have a clue that those were incorrect statements, even the journalists who think they know something about statistics. So I ran across a very neat little, here's then a correct statement, I think, more or less, subject to minor quibbles. But this is getting closer. And then, of course, the journalist will say, oh, okay, now I understand. And again, it's the wrong conclusion. So I ran across a very, and I'll do my example I didn't do last night because it was too complicated. I devised to try to explain to other people on my staff and other journalists what the issue is. So this is a diagram indicating how often I swim in the winter. And if you look at this, if it were properly constructed exactly to scale, which it might be, but anyway, it's supposed to indicate I swim less than 5% of the time in the winter. Consequently, if you, at some random time, asked me if I were swimming, and I said yes, the temptation would be, oh, I now have evidence that it's not winter because I only swim less than 5% of the time in the winter. P is less than 0.05 of this observation. Therefore, it must not be winter. Well, a lot of people think that's obviously correct, but if you look at how often I swim, the only time I swim is a few days in the winter when I go to